Right. So let us continue with our lecture 20, which is our final topics. Final topics for magnetostatic. Right. And next week going to proceed with the third parts of EMT, which is the time bearing. Yeah. So for the last topic of magnetostatic, we're going to cover the topics of inductance. Yeah, inductance, which is on the two things. Yeah, the first one is self-inductance, and followed by the mutual inductance. Yeah. Okay, a reference for this topic can be obtained from Sadiku, page of 387 to 390. Yeah. Okay. Right. So these are the objectives for lecture 20. The first one is to understand the concept of self-inductance and mutual inductance. Okay, and number two is to calculate the inductance value for a given inductor structure. Okay, so basically, the objective number one, I think it should be clear, which is we're going to differentiate the difference between the self-inductance concept and also the mutual inductance concept. And number two, we're going to calculate what should be the inductance value should be given any inductor structure. So basically, inductor or inductance, the concept of inductance is similar to the capacitance. Yeah, the capacitance that we have learned in electrostatic in the first part of EMT, in which capacitance is used to store the electrical energy. Yeah, we have learned this previously. And we have learned that in capacitance, in capacitance, you have learned that the C, the capacitance value, equals to Q over V. Okay, this is the equations of the capacitance that we have learned in electrostatic. And for the case of electrostatic or magnetic field, we also have a device, a component, which can be used to store the magnetic energy. Yeah, and the device that used to store the magnetic energy is what we call as inductor. And inductance is the properties. Yeah, is the properties of the inductor. Yeah, so basically, inductance and capacitance is the same. Is having the same function, which is to store the energy. Yeah, capacitance is for electrical energy, and inductance is for the magnetic energy. Yeah, so that should be the concept, the fundamental things that I think you need to understand. Yeah. Okay, so now we're going to proceed with the inductance. But before we can go for the inductance concept, I think it's good if we can first understand what is the flux linkage. Yeah, the flux linkage. Okay, so the flux linkage basically is the concept which is very useful, which is very important, particularly when we learn about the Faraday's law. Yeah, Faraday's law, in which I've assigned this as a group assignment to all of you. So flux linkage, if we can base on this slide here, is the fundamental concept that put a base, a base for the transformers functions. In which, if you base on this diagram, based on this diagram, we can see that if this is your current, this is your primary windings. This is your primary windings. I think you know what transformer is all about. The primary windings, and this is a secondary winding. So based on what we have learned in electrical circuit, I believe, or electrical machine, the purpose of these windings is basically to ignite or to produce the flux, the magnetic flux. And we have learned from previous lectures that when we have a current of I, so current of I will produce the magnetic field of H, which is we can use either the Biot-Savart's law or the Ampere-Circuitor law in approximating the amount of magnetic field that is produced by the current of I. Okay, and this current of this H field, which is produced by the I and the current, will then produce the magnetic flux density, the B, right? In which the B is equals to the mu of H, the flux density. And we have learned in magnetic material before, that depending on the mu, depending on the permeability of the material, we can produce the amount, the flux density amount that we want. So for the case of transformer, for the case of transformer, we wish to have the mu which is very large, because the idea is that you want to have a big amount of flux which can be linkage to the secondary winding. So basically this flux here is the linkage flux. Linkage flux, which is the flux produced from the primary windings, produced by the primary windings or produced by the primary current I1. So this flux here will be then linkage to the secondary windings, and which will be then induced to produce the I2, the induced current of I2. Okay, so basically we have learned previously that the flux, magnetic flux, and the B is related to the equations of magnetic flux equals to integrations of B dot ds. Okay, so this is where I mentioned just now that we need to have a huge number of permeability mu r, or mu, so that we're going to have a huge value of B, and as such we can have a huge amount of flux, magnetic flux of psi phi m, and the flux will be then linkage to the secondary windings as shown in the diagram. So this is what we call as a flux linkage. And the flux linkage basically is very important in the inductance concept, because I've used the words just now, the words of induce. The flux is linkage to the secondary windings, and from these linkage flux, it will induce the current of I2. So this is where the word inductance comes from. Induce, induction. Okay. And I believe that you're going to learn more about the induction current when you solve, or when you do the assignment related to the Faraday's law, which has been assigned earlier to you. So that's very important concept, the Faraday's law. Okay, so so this is the flux linkage in which we're going to use it in understanding further about the concept of inductance later on. Okay, so I did mention here that the induced EMF will be covered in the chapter, but however, as I mentioned to you, you have to learn this on your own, the induced EMF. If I can write for you the EMF, the equation of Faraday's law, equals to negative d psi m over dt. Okay, this is the equation of Faraday's law. EMF, which is the electromagnetic force, is equals to negative d psi m over dt. So d psi m, or psi m here, is the flux, magnetic flux, magnetic flux with the differentiation of flux magnet with regard to time, in which, if you base on this equation, the magnetic flux must be having a time dependent, must be having time dependent. So that's how we can have a differentiation of the magnetic flux with regard to time. The negative sign here is related to the Lenz's law. I believe that you have learned, you have some basic understanding what is meant by Lenz's law. So Lenz's law and Faraday's law needs to work together, need to exist together in understanding the behavior of the EMF produced. Okay, so that will be, I left this for you to solve, to be learned, in a group as instructed to all of you. Okay, so we can now proceed with the self-inductance. Okay, so I did mention just now that the origin of inductance is to be based on the flux linkage. And if we consider this particular structure, so we call this as a toroid. And in this particular toroid, we are having the N1 turns. N1 is the number of turns at one side of the toroid, and I1 is the current flow. In these particular conductors, right? And it said that the magnetic flux for the toroid, is proportional to the I. I think we know this, we have learned, I have mentioned just now that the I1 will produce the H1 will produce the B1, and from the B1 we're going to have the flux, magnetic flux. In this case, it will be psi m of 1. This is basically indirectly produced by the current of I1, Okay, so in this case, we can see that the psi of m is proportional to the I, because we know that B equals to mu of H, and H is having a proportional to the current of I, Okay, and if we base on this, we can have a general relationship between the flux produced and the current that produce it, in which we can have that the amount of flux will then be proportional to this current of I1. Okay, so basically we can define the inductance as the ratio between the flux produced, divided with the ratio between the flux produced and the current of I that produce the flux. So that's what we call as the self-inductance. So if I can rephrase it, if you based on this equation, if I can write it in terms of the N1 psi of 1, and this will be equals to L of I1. I just change the proportional sign to the equation sign, and from here we can have that the inductance of L is basically equals to the flux amount produced divided by the current that produced the flux. So that's how we define the self-inductance of L1. Self-inductance of L1. So L1, the self-inductance, is equals to the amount of flux divided by the current that produce it. Okay, so that's what we call as self-inductance. And the unit for the inductance is Henry. I think all of you know, the Henry, or just H as the unit for the inductance. Okay, right. So I hope that you understand now what is the self-inductance. So in short, we can just say that the self-inductance is the ratio between the flux, the total flux which is produced by the current, divided by the current that produced the flux. So that should be the self-inductance equation. So alternatively, we can also use the concept of magnetic energy to find the inductance. To find the inductance. I think this is similar to what we have learned previously in capacitance before. If I can rewrite here, that previously we have learned that the magnetic energy W of E equals to half integrations of D dot E dV, right? Okay, this is the equation for the energy in electrical field. Okay, and we have learned that in circuit theory that the energy or electrical energy produced by the capacitance or stored by the capacitance is equals to half of a CV squared. Half CV squared. C is capacitance value, V is the potential across the capacitor. So basically, these two equations are similar. In which you can see that based on this equation, we have half of CV squared shall be equals to half integrations of D dot E dV. So basically, we can find the capacitance C by simply having a ratio. C can be then equals to, so C basically equals to integrations of D dot E dV divided by the V squared. So that should be a technique, alternative method, which can be used to calculate the capacitance. Okay. So the same things apply for the case of inductance here, or the magnetic energy here. So we have learned that in previous lectures, we have come across this equation, I believe, half integrations of B dot H dV, which is the equations that can be used to calculate the magnetic energy density. And we have also learned in circuit theory before that the energy that is stored by the inductance or the inductor is to be based on this equation where we have half Li squared, in which L is the inductance value and I is the current that is passing through the inductor. Okay, and we can equate both equations here, both phrases, in which from this equation we can have half Li squared equals to half integrations B dot H dV, in which based on these equations we can then obtain the inductance value of L. So there are two options, two equations that can be used to calculate the inductance. The first one is by using the flux amount. The flux amount, we need to find the flux amount produced by the current, and in which we then need to find the ratio between the flux produced and the current, which will be the inductance value. And alternatively, the second method is that we need to calculate what is the amount of energy produced by the inductor, in which based on this equation, B dot H integration dV and divided by the I squared. So that should be the inductance value. So basically the answer for both methods should be the same. Yeah, so we're going to see in the example after this on how we can calculate the inductance based on method number 1, which is based on the flux method, and method number 2, which is based on the energy method. Yeah. Okay, so let's have this example number 1. Okay, any question before we proceed with example number 1 on the inductance so far? No, yeah? Okay, so for example number 1, we are having these problems where we have two long straight cylindrical conductors, each of radius A, are separated by a distance of D. So the conductors are used as a go and return circuit. It means that both conductors are having different direction of current. Yeah, direction of current. Okay, and the question is find the total inductance per unit length. Okay, so we don't have any detail on the sketching or on a graphical view of the problem, so we have to sketch it on our own. Yeah, so let's sketch it. Yeah, so we are given that we have two conductors. Okay, two conductors. We have conductors number 1, we have conductors number 2. Both are having same radius of A. Yeah, this is A and this is also A, the radius. And the distance between these two conductors is D. Yeah, so if we can put that D, which should be the distance between the center of the conductors. So that should be the D. Yeah, that should be your D, the distance between the conductors there. Okay, and it used to as a go and return circuit. So if we can assume that if we take this is the y-axis, that should be the x-axis. So your z should be in this direction. Yeah, yeah, we're going to have x, y, z. Okay, that should be the direction of the axis that we have. So it means that if we assume that for the first, let's say we label this as a first conductor, this is labeled to be a second conductor. So first conductor, if you assume that the current is directing in the positive z direction, so that should be the direction of your current. Across means that the current is going inward, yeah, towards the screen, whereas for a second conductor, it should be pointing in outward, in which it should be in this direction. Yeah, so the dotted line here, dotted point here means that your current is pointing outside, yeah, or away from the screen. Yeah, so that should be the direction of the current based on the given statement of the problems here. Yeah, right. So based on this, we need to find the inductance per unit length. Yeah. Okay. So basically, we need to calculate the inductance. Yeah. We go for the first conductor. Yeah. We go for the first conductor. Let's say we label the first conductor. We find the inductance produced by the first conductor. Yeah. Okay. So for the first conductor, we can say that there are two regions. Yeah. There are two regions. Okay. Before that, we assume that the current produced will be I. Yeah, means that this current, the current of I is said to propagate fully in this conductor of radius A. And the same thing is applied for the second conductor. We have also the same amount of I, but the direction of the current is different. Yeah. Okay. So if we consider first conductor, we can note that there should be two different regions of H field. Am I right? We have learned this previously. The first one is for the region of R. R is a variable, yeah? R less than A. Okay, R less than A. So we have the first region, R less than A. Yeah, note that we are referring only to the first conductor, yeah? And the second region is for the case of R, bigger than A, but less than D minus A. Yeah, which is outside the conductor. Yeah, which is from A to D minus A. Yeah, means that between these two conductors, yeah, the region between the two conductors. So we have two regions to be considered in this particular case. So why we have to consider two cases here? Because this is the regions where we have two different value of H field. Yeah, because when we have two different value of H field, basically we're going to have two different values of flux. Okay, so when we have two different value of flux, we are supposed to get two different value of inductance. So that's the issues there. Yeah. So it means that we are going to calculate two inductance value. The first one is the inductance for the region of R less than A. Yeah, and the second one is for the inductance for the region of R bigger than A, but less than D minus A. Yeah, so I put my point here that the needs why we have to calculate two value of inductance is because based on these problems, we have two regions of H field. Yeah, the first region is R less than A. Let's say we label this as H1. Yeah, H1. And then the second region is between A and D minus A. So we are supposed to get H2. So when we have two different value of H1 and H2, yeah, two different value of H field, we are then supposed to get two different value of flux. Let's say we label this as flux 1, we label this as flux 2. So when we have two different value of flux, we are supposed to get different value of inductance. So then we're going to have, this will be the L1 and that should be the L2. So basically, conductor 1 will produce two different values of inductance. We label for the R less than A, we label it as, okay, I think it's good if I can put L1 as L internal. Internal means that the inductance in the conductor. And for the L2, I just put this as L external, yeah, which is the inductance produced at the outside, yeah, at the outside of the conductor. Yeah, but basically both L internal and L external, both of them are produced by the same conductor number 1. Okay, right. So we're going to have two. The conclusion now is that from the first conductor number 1 here, we're going to have two values of the inductance, in which the L internal is the inductance calculated inside the conductor, which is less than A, while the L external is the inductance which is calculated outside the conductors. Okay, so the total inductance produced by conductor 1 shall be a summation of L internal and L external. Okay, so that's how we calculate the inductance produced by this conductor number 1. Okay, yeah? So we proceed with the first conductor number 1. I mean, the first conductor here, we go for the L internal first. So to find the L internal, we need to find the H1 first, the H1, which is the H field inside the conductor, yeah, having a radius R less than A, yeah. Okay, so this need to be back to the Ampere-Circuital law, yeah, Ampere-Circuital law, in which we need to use the closed loop integration of H dot dl equals to I enclosed, yeah, and this will give us H phi 2 pi of R, and the I enclosed will be I R squared over A squared, yeah, because the R is less than A, yeah, R is less than A, so as what I mentioned just now, I here is the total current that is flowing throughout this conductor, which is from 0 to A radius. So if you want to find the portion of current which is enclosed by a radius of R, yeah, radius of R, so the portion of current will be I R squared divided by A squared, yeah. So I think we have learned this previously in Ampere-Circuital law, yeah, so I think no need for me to repeat it, yeah. Okay, so as such, we're going to have that the H phi produced inside the conductor shall be equals to I R over 2 pi of A squared, yeah. So this should be your H field, yeah, the H field which is produced inside the conductor. So in terms of the vectors, it should be H vector to be equals to IR over 2 pi A squared direction of phi, yeah. Okay, so this is, I repeat, this is the H field produced in this particular region, which is for R less than A. Okay, so now once we have this H field, we can then use it to calculate the linkage flux, yeah, the flux linkage, in which we have learned that if we're having this particular radius, I mean the conductors of having a radius of A, yeah. So we can see that the amount of flux, yeah, the amount of flux, yeah, that will produce, yeah, if we have a radius of A of the conductors, so the amount of flux produced, wait for this, yeah. Okay, so if we have, okay, if we have a radius of A, pi A squared, yeah, which is the area of pi A squared. So the flux produced by this pi A squared shall be equals to integration from 0 to A of B dot ds. In this case, we have mu H, yeah, mu naught of H dot ds. Okay, because we are taking that the material here, there's no information about the medium, whether it's a magnetic material or free space. So we assume that it is just a free space mu naught. Okay, so that will be your flux produced in these particular conductors having radius of A. So if I can write it here, sorry, I need to use this space here. So if we have a pi A squared as the area for this conductor, total area, so we're going to have that the flux amount produced will be mu naught, yeah, mu naught. H will be integration of IR over 2 pi A squared, direction of phi, dot product with a ds, which will give us dr dz, direction of phi also, sorry, yeah. Yeah, because since your your H is in the phi direction, so your ds should also be in the phi direction, in which for the phi direction, it should be dr dz, yeah. So if you base on that, if you're not clear on how we choose that ds, it should be based on this rectangular structure, whether we need to use ds for surface number 1, ds for surface number 2, or ds for surface number 3. Yeah. So since the H is in the phi direction, so your ds to be used should be the ds of second region, I mean second surface. So for the second surface here, the ds should be dr dz direction of phi, yeah? Right. So based on that, you're going to have that should be the range of mu naught, yeah, I over 2 pi A squared, yeah, integrations of r dr d phi, yeah, in which the range of r should be from 0 to A, yeah, so going to have mu naught, sorry for this interruption, yeah, going to have mu naught I over 2 pi A squared. This is A squared divided by 2, and we're going to have a d phi over there. Sorry, dz, I apologize, not d phi, yeah. Sorry for this, yeah, my mistake then. Yeah, that should be the dz. Okay, the range of dz. Let's say we put that the range of z should be 0 to L. Yeah? We just put L as the range. Yeah. So for this, you're going to have that should be L. Okay, and this E squared can be cancelled out. So you're going to have mu naught I over 4 pi of L. Okay, so that should be your. Sorry for this interruption. Yeah, 4 pi of L. Yeah. Okay, so this is basically the amount of flux that we produce throughout these particular conductors having a radius of A. Okay, but if we are having smaller radius, yeah, if we are having smaller radius, for instance, if we have a pi r squared, yeah. So if I have pi r squared radius, yeah, in this particular case, yeah, pi r squared, in which r is the variable. So your amount of flux that we produce will be equals to pi r squared divided by pi a squared, through the integration of 0 to a of mu naught of h dot ds. Okay, so you need to calculate what should be the amount of flux that will be produced by this area, small area of pi r squared. Okay, so you need to calculate this. So let me redo this for you. Sorry for this interruption, yeah. Okay then. So basically, if you have pi a squared, that should be the amount of flux produced. So if we have pi r squared, which is a smaller area, so we're going to have that the amount of flux that will be linkage, it will be pi r squared divided by pi a squared integration from 0 to a of a mu naught of h, which is I r divided by 2 pi a squared direction of phi. Yeah, that should be the h, and the ds will be dr dz direction of phi. Okay, so then we can cancel out the pi here, and remember, yeah, that should be the amount of flux, yeah, that will be linkage. So the amount of flux will be then equals to mu naught I over 2 pi, yeah, a power of 3, okay, integrations of r power of 3 dr, integrations of dz. R is from 0 to a, z is from 0 to l. Yeah, so if we proceed with this, we're going to have mu naught I over 2 pi a power of 3. That will give us a power of 4, sorry, a power of 4, correct? Let me see, am I right? So this is a squared, yeah, sorry. This is a power of 4, this is a power of 4. So when we integrate it from 0 to a, we're going to have a power of 4 divided by 4. That should be L. Yeah, so a power of 4 can be cancelled out. So end up we're going to have mu naught I divided by 8 pi okay. Okay, so we're going to have it as mu naught I over 8 pi multiplied with L. So that should be the amount of flux that is produced for the region of R less than A. Yeah. So based on this, we can calculate that the inductance of L shall be the amount of flux divided by the current of I. Okay, and remember that this is the L internal, yeah? So I just put it as L internal. I'm very sorry for this interruption. I'm not sure what happened to my tab here. Always produce the line. Yeah, I'm not sure why. Sorry for that. So we have L internal to be the flux amount divided by the current of I. That should be based on mu naught over 8 pi multiplied with L. And since the question asks us to find the total inductance per unit length, so I need to bring the L to the left hand side. So end up going to have L internal divided by length shall be equals to mu naught divided by 8 pi. Okay, so this is the amount of flux that is produced inside the conductor. Yeah, the amount of this is the amount of inductance per unit length that is produced inside the conductors, yeah, having a radius of A. Okay, so we have done with the L internal. Yeah, L internal. Any question before we proceed with the L external? Yeah, so just to recall, just to remind you that for the conductors here, we are having two values of the inductance, The first inductance value is for region of R less than A, which has been calculated here. This is the amount of inductance per unit length calculated. Yeah, and for the L external, we're going to calculate after this. Yeah. Okay. All right. I'm going to use a second method. This is the first method, which is based on the flux amount. Yeah. But I'm going to use a second method, which is to be based on the energy density. Yeah. Okay. For the energy density, yeah, we have learned before that from half integrations of B dot H dot dV. Okay, half of B dot H dV. So this is equals to half of Li squared. Yeah. Okay, and from here we're going to have L shall be equals to integrations of B dot H dV divided by I squared. Yeah. Okay, so we have learned before that for R less than A, we have learned that the H field is equals to I R over 2 pi A squared direction of V, right? Okay, so from here we can have the integrations of mu naught of H squared, which is I squared R squared divided by 4 pi squared yeah, 4 pi squared of A power of 4, yeah, this is H squared, yeah, right? And the dV basically will be R dr dv dz because we are dealing with the cylindrical system, and that should be divided by the I squared, yeah. Okay, so when we proceed further, I squared can be cancelled out. So we are going to have mu naught over 4 pi squared of A power of 4. So integrations of R power of 3 dr, integrations of dv, integrations of dz. So R is from 0 to A, yeah, which is for R less than A, yeah. This is calculation is for R less than A. Okay, and the phi is from 0 to 2 pi, whereas z is from 0 to L, the length of the conductors. So we are supposed to get mu naught over 4 pi squared A power of 4. So that will give us A power of 4 divided by 4. So that will give us 2 pi, and that will give us L, the length. So a few things can be cancelled out. E4 can be cancelled out, pi can be cancelled out, 2 can be cancelled out, and end up going to have mu naught divided by 8 pi multiplied with L. Okay, so basically this is the inductance, yeah, the L inductance. The inductance here, because it is for R less than A, so we call this as the L internal. Yeah, and to find the inductance per unit length, we can have that the L internal divided by the length shall be equals to mu naught over 8 pi, which is similar to what we have obtained previously. Okay, so this is the method on how we calculate the inductance for the first case, which is the internal inductance. Okay. All right. So we now proceed with the second region. Mean for the region of R bigger than A but less than D minus A. Yeah? So if you can recall back, this is outside the conductors. Yeah, outside the conductors. Okay, so we're still dealing with the first conductor. If you can recall back, first conductor is on our left hand side just now. Okay, so basically this need to calculate the H field. So the H field will be based on the Ampere's second law, the I enclosed. So we're going to have H P of 2 pi R. So the I enclosed basically will be I. Yeah, I don't think I have to do it for you for this case, because I believe that all of you have understand clearly on the Ampere's second law. So based on that, we're going to have the H phi will be I divided by 2 pi R, yeah, and here we're going to have the H vector will be I over 2 pi R direction of phi, ampere per meter. So this is the H field for the region of R between A and D minus A, yeah, which is outside the conductors. So from here, we need to calculate the magnetic flux, yeah, because we want to find the inductance, right? So the magnetic flux produced from this H will be flux magnet, be integrations of B dot ds, yeah, and this will give us mu naught of H dot ds, okay, and we're going to have it as mu naught, okay, H will be I over 2 pi R direction of phi, and in this particular case the ds can be calculated simply as a dr dz, yeah, dr dz direction of phi. Okay, and we can then proceed with the calculation of your magnetic flux, yeah, in which we're going to have mu naught, I is taken out over 2 pi, then we have 1 over r dr integrations of dz. Okay, remember that your range of R is between A and D minus A. Yeah, so you have to put that the range of R here will be from A to D minus A. Yeah, remember, yeah, if we can sketch it for you again, that should be the two conductors that we have. Number 1, this is the A. Number 2, that should be the A. And the range, the distance between the two conductors is D. Okay, so the region that we are considering now is this region here, yeah, between the two conductors, yeah. That's why we need to put the range of R, the range of integration will be from A to D minus A, yeah. And the length of Z is taken from 0 to L straight away. So based on this, we can find that the magnetic flux will be mu naught I over 2 pi, so that should be ln of D minus A divided by A and length of L. Okay, so basically this is your flux magnet, which will be then used to calculate the inductance. So we're going to have L external can be equals to the flux magnet divided by the current of I, which will be based on mu naught over 2 pi ln of D minus A over A times L. And if you want to find the inductance per unit length, we're going to have L external over L should be equals to mu naught over 2 pi ln of D minus A over A. Yeah? So that should be your inductance per unit length, but for the region of R between A and D minus A. Okay? So for this, we can then calculate that the total inductance, I put this total inductance over length should be L internal over L plus L external over L, which will be mu naught over 8 pi from the previous answer plus the present answers, which is mu naught over 2 pi ln of D minus A over A. So that should be the total inductance per unit length produced by a single conductor, right? A single conductor. So to find the total inductance, yeah, because a second conductor will be producing the same amount of H field, because the reason why is because the direction for both current are different. Yeah, this is towards negative Z, towards positive Z, sorry, and the second conductor is towards negative Z. So if we use a right-hand rule, basically for the first conductor, your field, H field will be in this direction. This is H1. And for conductor number 2, knowing that the current is directing towards negative Z, again, your H field will be in this direction also, which is H2. So due to this, we can understand that the total H field, yeah, both will producing the same H field amount. Yeah, and you're going to have that the total inductance produced by these systems of conductors will be just the value that we have here multiplied with 2, in which, if I can put it here, that total inductance, yeah, total inductance per unit length produced by the two conductors here will be simply 2 multiplied with mu naught over 8 pi plus mu naught over 2 pi ln of D minus A divided by A. Yeah, so that should be your total inductance produced by these two conductors here. Okay then, right? So this is based on the method of flux, yeah? Method of flux. So we can do the same things for the case by using the magnetic energy method that we have mentioned just now, yeah, that we have used just now for the case of the internal inductance. Yeah, if I can do it for you, for the case of the a region of R between A and D minus A, we can have that the energy will be half integrations of B dot H dV, and that will be half of a mu naught, yeah, mu naught of H squared dV. So we're going to have half mu naught. So H squared will be I squared over 4 pi squared of R squared integrations, yeah, and dV will be R dr dphi dz. So we're going to have mu naught I squared over 2, yeah, and then will be, will be 8 pi, yeah, 8 pi squared, yeah, and that will be 1 over R, yeah, 1 over R dr. Integrations of dphi, integrations of dz. R is from A to D minus A here. That should be the range of R that we have. P is from 0 to 2 pi and Z is from 0 to L. So we proceed further. We're going to have mu naught of I squared. Yeah, and that will give us 8 pi squared. So that will give us ln of D minus A over A, and that will give us 2 pi, and L should be there. So a few things can be cancelled out. Pi and pi, 2 and 8, we're going to have 4 there. So that will give us mu naught I squared over 4 pi ln of D minus A over A times L. And this can be then equated with the equation of half Li squared. So basically mu naught I squared over 4 pi ln of D minus A over A times L shall be then half of Li squared. Yeah, so you're going to have that the L, so in this case should be L external, yeah, which is for this region. So that should be L external. And you're going to have mu naught I squared, okay, divided by 2 pi. Sorry for this interruption again. 2 pi should be there. Yeah, because cancel out with this, you're going to have 2. Right, and then we're going to have ln of D minus A divided by A divided by I squared. So can be cancelled out still. So we're going to have, sorry, L should be there. So we're going to have L external over L shall be then equals to mu naught, okay, ln of D minus A divided by A, L divided by 2 pi. So that should be the equations of the inductance per unit length for a region of R between A and D minus A. So this is the alternative method which can be used to calculate the inductance. Yeah, so you can opt for the flux, yeah, flux method, in which you need to find the flux, yeah, and then divide with the current, or you can just base on the energy, kinetic energy for us to find the inductance in this case. Okay, right. So the answer obtained by this method should be similar, yeah. Okay, any question for example number 1?
Doctor, can you explain again why the L total per length of the two conductors are the same?
Ah, okay. Okay, I need to erase this, yeah. This is not then. Okay, we go back to the structures of the current of the conductors, yeah. So this is your conductors, okay. So the first conductor is having direction of Z, yeah. If we're taking that this is X, sorry, if I take this is Y just now, Y, that should be X, and that should be Z direction, yeah. So it means that for the first conductor here, the current I in this conductor is pointing towards positive Z, whereas for the second conductor here, yeah, I put this at number 2. For second conductor, the direction of current is towards negative Z, yeah. Okay, you got the point there, yeah? This is positive Z, this is negative Z direction. Okay, so by using the right-hand rule, we know that the field produced by the first conductor supposed to be in this direction, right? That should be the H produced. Am I right then? Behind?
Yes. Yes.
Okay. Okay, so that's why from here we can have that, yeah, by having this H, we're going to have that the L total per length is based on the blah, 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 the equation that we have produced just now. So the same thing's applied for the second conductor, okay, second conductor. If you base on the right-hand rule, we can know that your field direction should similar, right? This direction.
Yes.
Okay, so if we base on this, we can know that the amount of inductance produced should also be the same as the first one. Okay. All right. Okay. So based on that, we can simply add them together. So the first inductance per unit length plus second inductance per unit length. So that should be the total inductance per unit length produced by the system. But if you're having a problem whereby for the second conductor, the current is having same direction. So what do you think, Behan, will happen?
Zero.
Correct. Correct. Yeah. Because why? Because if you base on the right-hand rule, what should be the direction of your field produced by the second conductor? It should be
opposite direction.
Yeah, correct. That should be the H direction, the H2. So it will cancel out. Yeah. So when the field cancel out, which means that the flux which will be cancelled out, and as such, there should be no inductance. Right?
Okay, thank you.
Okay, okay, welcome. Okay, then I think it's clear on this example number 1. I hope there should be no more questions on this, yeah? Okay, example number 2. Example number 2 is basically related to about the same problems, yeah. But the difference is that we are having values to this. Yeah, given that we are having two copper wires having 2 millimeters diameters for both copper wires. Yeah, placed parallel in air with a separation distance d between them. If the inductance of each wire is 1.2 microhenry per meter, okay, calculate the internal inductance and external inductance parameter for each wire. And number 2, calculate the separation distance D. Okay, so basically the problem is similar to what we have done earlier, for example, number 1. Yeah, so we just need to re-sketch the diagram. For example, number 2. So we are having the same the first conductor there. Then we are having the second conductor here. Okay, the wires is having diameters of 2 millimeters, so the radius will be 1 millimeter. Yeah, both are having same radius. Yeah, this is 1 millimeter radius, and the separation between the two conductors is D. Yeah, is D. Okay, so that should be the separation of D between the conductors. Okay, it's given that the inductance of each wire, yeah, of each wire means that inductance due to conductor number 1, yeah, conductor number 1, yeah, inductance L total per unit length, yeah, because this is microhenry per meter, so it is equals to 1.2 microhenry per meter, in which we know that for this particular problem in which we have we did this in the example number 1 just now, in which we are assuming that both are having different direction of current, yeah, because it's given here that inductance exists. So when the inductance exists, it means that the current should be having different direction. So we assume that, for example, we assume that this should be in this direction, and second conductor should be having this direction, so which is opposite. Okay, and in this case, we can say that this equation of total inductance per length will be actually comprises of L internal per length plus L external length, and that should be equals to 1.2 microhenry per meter. I'm very sorry about this, yeah, very irritating. Okay, okay, per meter, yeah, per meter. Okay, so this is what requested from the question, yeah, which is to find the internal inductance and external inductance. Okay, so I think we can go do it one by one. We go for the internal inductance first because this is similar. So previously, from the previous example, we have calculated that the L internal per unit length basically will be mu naught over 8 pi. Yeah, and if you base on this calculation of mu naught, which is 4 pi times 10 power of negative 7 divided by 8 pi, this can be cancelled out. Pi and pi, this is 4 and 2, 8 can be cancelled out. So we're going to have 0.5 times 10 power of negative 7, which will give us 0.05 microhenry per meter. Yeah, so that should be our internal inductance per unit length. And as such, we can say that the external inductance per unit length will be simply the total inductance per unit length, which is 1.2 microhenry per meter, which is based on the given information in the questions, minus the internal inductance per unit length using this equation. Yeah, yeah, this is minus 0.05 microhenry per meter. So end up we're going to have the value of these external inductance per meter shall be equals to 1.15 microhenry per meter. Okay, so that should be the answer for number 1, in which internal inductance, which is based on this equation that we have seen before, shall be 0.05 micro, whereas for the external inductance per meter, which will be a subtraction between the total inductance and internal inductance, will be simply 1.15 microhenry per meter. Okay, I think that should be a very straightforward technique to calculate, to answer question number 1, in which the information that we have obtained from example number 1 is used in this example number 2. Okay, and then the question number 2 is to calculate the separation distance D. Yeah, separation distance D between the two conductors. I think This can also need to be based, this can also answered based on the previous example number 1 equation. We have learned just now that the L external per unit length is equals to 1.15 microhenry per meter. And we have seen before that the equation for the L external per length for one wire, for each wire, for one wire, so that should be equals to, let me see, what's the equation just now? Okay, it should be mu naught over 2 pi ln of D minus A divided by A. So this should be the equation of external inductance per unit length, and that should be equated with 1.15 microhenry per meter. So from this, I believe that you can use it to find the D, because A is known. A is simply 1 millimeter. So let us substitute mu naught. Oh, sorry, I apologize. I need to rewrite this for you. Okay, sorry for that. So this will be, just now is 1.15 micro. The equation will be mu naught over 2 pi ln of D minus A over A, 1.15 micro. Okay, and that will be 4 pi times 10 negative 7 over 2 pi ln of D minus A over A equals to 1.15 micro. So this can be cancelled out, the 2. Okay, and then we're going to have, this will be 0.2 micron, I believe. So that should be ln D minus 1 millimeter over 1 millimeter equals to 1.15 micrometer divided by 0.2, 0.2 micrometer. Okay, so from here we can see that D minus 1 millimeter over 1 millimeter shall be equals to exponential of 1.15 divided by 0.2. Okay, so I think I left this for you to calculate the D, So I think you can calculate the D on your own. So what should be the value of D based on the solution for these algebraic equations here? So that should be the D, the separation distance between the two conductors. Okay, any questions for this straightforward example on the self-inductance so far?